You'll hear ho, ho, ho. On Christmas Day, you'll wake up and you'll say, hooray for Santa Claus.
Hello and welcome to day 15 of Advent of Code. I'm really feeling it tonight. Pretty optimistic about it. I think this is the night that we finally break into the top 100. But you know, it's going to depend on what kind of problem it is and mistakes and the approach that we take, the algorithm that we choose. Hopefully it doesn't take an hour like it took yesterday. Here we go. Dueling generators. All right. Trying to agree on a sequence of numbers. One's malfunctioning. They don't match. Judge. All right. Compares. Keeps track. Number of times they match. All right. To create its next value, multiply it by a factor. Then keep the remainder of dividing that. All right. So, all right. So we're going to need these numbers here in the program. Okay, so it keeps, all right, so this is going to be, so we'll use iterate. All right, to calculate the first value, you need to use a specific starting value as its previous value. Okay, all right, so, okay, so we might def in some function here, gen, on a number here that then a, some number that multiplies in by this and takes the remainder of this, and similarly gen b, its value is here, right? Okay, binary. All right, here you use the lowest. Okay, to get what is the judge's final count after 40 million pairs? Okay, so I think, so let's see, so we got to get the puzzle input. All right, so we know that we're going to do something like iterate gen A starting here. And then we're also going to have iterate gen B starting here. Okay, and then we're going to have some match here for values A and B, where, so because of this one match, this is basically, is it the case that the 16 lowest bits are the same? So is it the same? Is it the case that bit and A from, let's see, can I do 16 lowest bits should be like that, I think. Yeah, 255. Bit and B, 255. All right. And then yeah, so I think we don't want to take the first value from here. First value. So I just think that we need to take rest here. Okay, so this, we got our matcher, and then we want to, I guess, maybe do like a filter on M. Here we go. We'll map M to this. Take 40 million and get the frequencies out of this. Judge would like to consider 40 million pairs, eventually finds a total in here. All right, and then while this is running, connect another REPL, I guess. Keep an eye on this first one. 40 million. All right, so we got this many true values. Not the right answer. Okay, so let's see. So if Gen A uses 65, and I guess let's just do a quick question of whether this matches this here. So that is false. Okay. All right. So let's just see if Gen A on 65 produces the right. Okay. So it does. Take 5 here. Iterate. Yeah. All right. Okay. Those values look good. Okay. So if we say Gen A 35 and 8921, 65, 8921. All right, so let's see. The judge, okay, because of this one match, 1 to its total, judge would find a total. What is the judge's final count? Okay, so just make sure we're calculating this correct. Okay, and then here we're going to take 5 of these. Right, that does seem to get the right answer. And it would eventually find a total of 588 pairs that matched. Well, I mean, I can run the same code for 65 and 8921 and see if the answer produced is the same as what it's saying. But yeah, I mean, 255 is 8 bits. This is just bad. Yeah. There we go. Okay. Okay, much better definition here. Run this again. All right, much lower number. Not the right answer. Huh. That's actually surprising. The lowest of the 3, because of only this one match. Well, okay. I guess let's run it against the test case here. It's supposed to be 588. 40 million. Yeah, we're doing 40 million. All right, so this is wrong. What so what is wrong about this? This should take the lowest 16 bits, and this should also take the lowest 16 bits. Am I missing? Oh, yeah, that is a bug. All right. Yeah, just yeah, the dangers of using decimal representations of numbers is you might type a 6 where it needs to be a 5. Okay, new number here. The right answer, rank 222. All right, let's try it. Let's hope that part 2 is hard. Let's see. Okay, the generators get more picky. All right, generator A looks for values that are multiples of 4. Generator B looks for values that are, okay. Each generator functions completely independently. Okay, only occasionally okay. Pretty cool. Yeah, so basically, let's see. So we would kind of want to do like some kind of iterate on a function like this, starting with this value. Take the rest of them filter on the remainder needs to be, the remainder of this value by 4 needs to be 0, and take the first of these. All right. And then we basically want the same structure over here, except this one is looking for 8. All right, so change gen A, change gen B, and run our code again. Wrong number of, right. This needs to be changed. Good. Okay. What? Wrong number of args passed to, right. Yes, we actually have to give it a starting value here. Okay. Yep, that was wrong. And okay, this is looking much better. All right, kick it off. And yeah, if these numbers are co-prime, then the program, my guess, is going to take 8 times as long to run, because we're going to be effectively bound by the behavior of gen B here. So probably paying a pretty steep penalty for just using naive closure here. Yeah, on the plus side, JVM math is pretty fast. So I guess it really just depends on how much boxing and unboxing is going on. Yeah, first time I think it was taken like around 30 seconds or so. So we're talking about it taking like 4 minutes now. All right, that's it's not horrible. Yeah, let's see if we need to make this faster. What would the place to be? Where would be the place to put that? So yeah, not sure. This M should be pretty fast. Yeah, this is something that would be probably be a lot better represented in something like Java, where like your generator could just be like an actual Java object. Okay, here's an answer. All right. Not the right answer. Okay, did they change something about the 5 million pairs? Yep. Not reading. That does, yeah. That makes a difference. All right, new answer. Here we go. Submitted. Wait 27 seconds, it says. All right. 14 seconds. 3 seconds. And here we go, rank 210. Okay. So no points tonight. Let's talk about the problem. So yeah, basically this was a pair of generators problem where there are 2 generators that are just producing, they produce a sequence of values, and you need to pop values off off each of the generators and then compare them and then count the number that compared successfully. So algorithmically, very straightforward. I think that there's a lot of optimization to be done around like how the math is done and things like that. But yeah, so the implementation that I started with for generators was I just implemented a generator as a function from the last input that it had, and then I ended up using the iterate closure function. So one snag there is that I had to call rest on it because the generator doesn't actually produce its starting value. So you have to sort of drop that part of it there. And then yeah, just call map on this. So map actually handles popping off both of the collections. It's fine that this whole thing is infinite and, because it's lazily evaluated, and this does go through a take. So this limits it, and then frequencies just sort of gathers up the values. My implementation of M was wrong twice, and that's what cost me. So initially, why did I think that it was 256? I think I figured, I must have figured that like each hex digit was 8 bits or something. But yeah, that's obviously wrong. If you want to take the lowest 16 bits from a number, then then you need to bit and it with hex FFFF, which is this here. And then what did I do? Oh yeah, and so instead of having the REPL to give it to me this way, I asked the REPL to give it to me this way. So I grabbed this value, copied it, and pasted it in here, and then knew that I had to actually go back and adjust this by setting that 6 to a 5. And then when I did that, I just didn't set it properly. So so that caused me to lose a lot of time. Yeah, I may go back in and see how close I was if I hadn't made those mistakes. How close I would have been to getting in the top 100 for tonight. But yeah, part 2 makes it a little bit harder and then a little bit easier, which I wasn't expecting it to be made easier. But yeah, this is just basically a filter on each generator. I think they were probably, yeah, just looking to maybe trip people up if the generators sort of aren't defined. Yeah, I can kind of see that. If the generators sort of aren't defined as independent things, then I can see someone having trouble with part 2. Like if you don't reify the generators, if you just sort of represent their state and then do like, you know, arithmetic inside the main loop of your program, then you might have trouble with this refinement, because now they just have different it takes them differing amounts of iterations in order to produce like their next value. Yeah, I do wonder if Google will give me the lowest. So if Google will tell me whether 2 numbers are co-prime, because if they were, then I think you'd be able to. I think that you wouldn't have to actually do a check on whether these values are multiples, because it would be regular. And yeah, maybe mathematically, actually, it doesn't matter either. In fact, yeah, it doesn't matter. So basically, if you actually just looked, so this is interesting. So if you just take, say, 5 from here, like say like maybe 10 from Gen A. Hang on, okay. So let me define Gen A back to be. Okay, so Gen A is going to be just take the input here and do it the old way. So if you just look at this and then you map what is the remainder of this value by 4, then let's see, let's take 100 of these. Let's see, I'm expecting this, I was expecting this to have a regular pattern that I would understand. But staring at it now, nothing immediately pops out at me. That can't be true. It's just not. I mean, it can't be. It can't just be random, can it? Like 1. So shouldn't there be like another 0, 1, 1, 0 in here? But I don't see it. Huh. Well, maybe this is some kind of pseudo-random number generator. Yeah, that's interesting. I was kind of predicting like if these two numbers were like, okay, I think I see what's going on. I think it's the fact that this number here is so much larger than this. No, that doesn't seem right either. Like if these numbers were something like 17 and 31, let's say, then I would kind of expect this to have a regular structure. 2, 2, 1. Maybe it does, but I'm just not seeing it. So in any case, yeah, I doubt I was going to do derive a proof of all that faster than I could just tell the computer to just check each of these for whether it was divisible by 4 or by 8. So straightforward stuff. And then, like I said, the problem is also made easier by only needing to consider 50 million pairs, which I missed the first time. So that cost me time twice. First by the program just taking longer to run, and then second by producing the wrong answer. So yeah, couple of mistakes that kept me out of the top 100. But quick night. Our advent calendar is filling up. We only got 10 more days to really show our stuff. So I'll be back at it tomorrow. Actually, I'll be broadcasting from my company's holiday party. So that should be a lot of fun. We'll have some of the brightest minds in the industry contributing to coming up with a fast solution. So see how we do there. And so I hope that you tune in tomorrow. And if you've tuned in tonight, then thank you for watching.
S-A-N-T-A-C-L-A-U-S-A-R-A, for Santa Claus. Spell it S-A-N-T-A-C-L-A-U-S-A-R-A, for Santa Claus.